Welcome back to Industrial Problem Solving. My name is Dave Roysum. In the last module, we gave you 8 ways you can get stuck. Your job was to recognize those pitfalls as early as possible and avoid them as best you can. Here, we add another half-dozen pitfalls centering around contaminated data and poor analysis techniques. Be a fox. See and smell and hear trouble ahead. Avoid it if you can. In logic, the next major section of this course, a premise is a statement that is taken to be true for the purposes of argument. Best practice is that the premise is explicitly stated. Best practice is that the premise is checked sometime soon, though not necessarily at this point where hypotheticals are allowed. In problem solving, we have the same issues. We should state assumptions explicitly and check our assumptions against several different lines of evidence. This can avoid some serious embarrassment and worse later on. The trouble is that checking assumptions can get you into serious people problems. Imagine saying to your boss, "Assuming you are correct, sir," when you say we should work on X. Imagine challenging the boss to show multiple independent lines of evidence to support her conclusion that the problem is worth working on. Much diplomacy would be needed in any of these cases listed here. In many cultures, and with many people, you may be better off by just quietly checking the assumptions on your own and not verbally challenging others. Of this list, I want to call attention to one very important assumption that must always be checked. That is, if the information you are being given is correct. Very often what you are told is incomplete or irrelevant at best, and at worst, completely incorrect. In an earlier module, we covered secondhand reporting that may come from, example, customer complaints. Very often, the sensors and measurements we have are not good enough to make conclusions, either because the sensor does not have sufficient resolution or that the sample size is too small. Sometimes the trial is poorly designed so that you have statistical confidence all the while the conclusions are bogus. Pause the tape, read, reread, and meditate on all the ways you can get stuck by making assumptions. Add to this list even more ways that you've seen in your work or home life. Continuing with our theme of commonly contaminated data is the statement, "We've never had that problem before." I often get that as a consultant, perhaps more than you. When I hear this, I first think to myself, you probably had that problem since day one. But that now someone, probably a customer or bean counter, is complaining more than before. Perhaps you have a thinner web and it is giving you more trouble than the thicker web where the waste rate was tolerably low. One workaround is to challenge a long-time operator by asking, "When is the very first time you ever saw this?" This will likely trigger their pride in their knowledge, and they will likely confess that the problem was always there on some grades. Continuing again with our theme of commonly contaminated data is the statement, "We didn't change a thing." Everyone has heard this as people try to distance themselves from blame. Finding out what might have changed will challenge our 20-question skills that we talked about in a previous module. However, as we will see shortly, this approach itself might be a very poor problem-solving technique. Unfortunately, this desperately weak technique is probably the most commonly used in industry. There are times that a machine performed well enough. That can lead us to a paralyzing thought pattern I call the sweet spot. Here, the thought is to try and get back to that sweeter running condition by doing something easy, such as turning a knob, instead of something more difficult but possibly more effective, such as firing your supplier who's giving you baggy webs, or replacing part of your machine, which isn't good enough. Note, we are not saying that problem solving via turning a knob is not desirable or even preferable. It is just don't count on it. If there truly were a sweet spot, you should have already found it and be running there if it were practical. Here are some common response curves. They would, for example, represent defect rates versus a knob setting. In most cases, there is simply no sweet spot. In other cases, you should have already found that sweet spot if it were truly noticeably better, and you were allowed to move that knob. Please, pause the tape, study these curves, study them again, and meditate on why pleasant knobs might not yield a pleasant solution. Unfortunately, we can't predict who's going to get cancer. We don't have enough knowledge or data. Yet, we do know many useful things about the risks, such as smoking significantly increases the incidence of lung cancer. Unfortunately, we can't predict when and where the next earthquake strikes. We don't have nearly enough knowledge or data. Yet we do know that living near a fault line is a major risk, and we know a bit about earthquake-resistant buildings. Yet, in industry, we are often asked why one machine or even one roll will have a defect and the other not. Indeed, it is a very common line of questioning, and some problem-solving methods are based on this extremely weak methodology. Let's take a couple of examples and see what kind of trouble we can get into. So, let's assume that machine Y truly runs better than machine X. Let's also assume that we know this for certain with statistically compelling data. What could be the reason? If you think about it a bit, you will note there are hundreds or thousands of differences between any two machines, even if they are duplicates. Yes, on many occasions, I've seen two side-by-side machines made from the same prints and running the same raw material, and yet have notably different runabilities. How are you going to approach this problem? You simply do not have the design of experience energy to change one part at a time and see which one or ones made the difference. Let's take another very common example. Let us assume that one material, perhaps your competitor's material, reportedly runs better than yours. If we think this is true, think again. It would be an unstated assumption that the reporting from the customer was true. Or, even if it were true, The competitor's material might be better in one attribute, but worse for another. So what? What are you going to do with this information? We simply do not know how to change one property and not change any other properties. All this comparison does is to tell us that one material might run better or even well. We learn nothing new because we already knew that one material is likely to be better in one attribute than another material. We learn nothing useful because we don't know which property is the one that matters and have no way, short of established scientific models, to find out which one it is. Comparisons are unavoidable. If you don't bring them up, someone else will. So how do you deal with them? If you are so fortunate to have a solid, applicable, science-based model of behavior, you may be in decent shape. Hopefully, science and experiment will both tell you which parts or which properties are most responsible. If not, we should try and steer around the pitfalls of comparisons. Yes, it is okay early on in the brainstorming part of process. Comparisons may help get the thinking juices flowing. When it may become a waste of time is if you spend much effort on getting the answer. The odds are very much against it. Instead, politely and politically ignore the question. Maybe it will go away long enough for you to do more useful troubleshooting, as we discussed earlier in this course. Thank you so very much for joining me in this problem-solving process. I hope I've made the case that there are many ways to get stuck, and that looking ahead and avoiding trouble when possible is preferable. We covered a half-dozen quite common cases of these sorts of troubles here in this module. We have another dozen yet to go. Stay tuned for more ways to avoid getting stuck.